Hey guys, welcome back to the channel. Today we're going to talk about something super interesting. What happens when those tiny particles, electrons and positrons collide? So, imagine you have an electron, right? And then you have its opposite, its antimatter buddy, the positron. Now these two can interact in a couple of cool ways, called Bhabha Scattering and Electron-Positron Annihilation. These fancy names come from quantum electrodynamics, or QED, which is like the rule book for how light and matter interact. First, let's talk about Bhabha scattering. It's like a game of cosmic dodgeball. The electron and positron throw a photon at each other, kind of like a ball of light, and then they bounce off in different directions. There's still an electron and positron after the interaction, just like how after playing dodgeball, you're still you. Now there are two ways this dodgeball game can go. They can directly throw the photon at each other, or they can do something even cooler. They can briefly become a photon together and then quickly split back into an electron and positron. It's like a magic trick. Now let's talk about the more dramatic one, Electron-Positron Annihilation. Imagine the electron and positron are like matter and antimatter bombs. When they collide, they completely destroy each other in a burst of energy, transforming into photons, which are like tiny packets of light. Sometimes, if they collide with a lot of energy, they can even create heavier particles like muons, quarks, or even Z bosons. These are just more exotic and heavier particles that physicists love to study. So how are these two processes connected? Well, remember that cool trick where the electron and positron briefly become a photon in Bhabha scattering? That's actually the same physics happening in pure annihilation. The only difference is what happens at the end. Now, let's rewind the clock way back to the beginning of the universe, just after the Big Bang. Back then, electrons and positrons were everywhere, like a giant cosmic soup. They were constantly colliding, annihilating, and being created. Bhabha scattering was super important because it helped keep everything balanced in this chaotic soup. As the universe cooled down, most of the electrons and positrons decided to annihilate each other, creating a massive burst of light. This light is actually still visible today, and is called the cosmic microwave background radiation. It's like a baby picture of the universe. So why should we care about Bhabha scattering? Well, it played a crucial role in making the early universe the way it is. It helped distribute energy evenly, and ensured that everything was in balance. By studying these processes, we can understand how the universe evolved from a hot, dense soup into the structured cosmos we see today. And here's a big mystery that Bhabha scattering might help us solve. Why is there more matter than antimatter in the universe? It's like wondering why there are more right shoes than left shoes in the world. By studying these interactions, we can get closer to understanding why our universe is filled with matter and not just a whole lot of nothing. So there you have it. Electron-Positron Annihilation and Bhabha scattering are not just some abstract physics concepts. They're key players in the grand story of our universe. They helped shape the cosmic microwave background, influence the balance of matter and antimatter, and continue to teach us about the fundamental laws of nature. That's it for today's deep dive into the quantum world. If you enjoyed this video, don't forget to give it a thumbs up and subscribe to the channel for more awesome science content. Until next time, keep those brains buzzing.